A very important concept in computer science and computer engineering, especially if you want to go on to design hardware and circuits and whatnot, is the concept of algebraic logic. Now, essentially, there's a way to take this entire statement and reduce it to a much cleaner, much easier, and much less expensive implementation. So suppose you're sitting in a second year digital systems class and your professor on the exam asks you to reduce this logically. So what you want to do right off the bat is look for the most well-distributed term. And right here, that is B. It's in everything. So we can pull B out, and this is exactly the same as regular algebra whenever you are pulling out a variable that's well distributed across every term. So right off the bat, we can say A naught, try to use the same terms as much as possible, A and C and D, or A and C and D naught, or A naught, C and D naught, or A and C naught and D. Well, looking at this for a minute, you see now we have a new term that seems to creep up every now and then. That is this one, A naught C, A naught C. So we can actually pull that out thanks to commutative laws. We can say A naught C. And so what's the leftover term here and here? Well, that's D or D naught. Now, moving on, we see we have A and C and D naught. We have A and not C and D. So here we have a distributed A. We can pull that out, and then we can include these remaining terms to say C, D naught, or C naught and D. Well, now we have a situation where we have a variable ORed with its negation. So whenever D is 0, D naught is going to be 1. And whenever D is 1, D naught is going to be 0. But either way, you twist it, it's always going to be 1. So, in fact, this whole term can be reduced to 1, which means it's always true. You can actually disregard this whole thing and just leave it out, and I'll show that in a minute. Now, we look at this inside term, and we see something peculiar. C and D naught, or C naught and D. So whenever C is 0 and D is 0, D naught will be 1 and C naught will be 1. But because we need 0 and 1 or 1 and 0, there's no term in this combination that is actually true. But what if C is 1 and D is 0? Well, if C is 1, then C naught is 0. But if D is 0, D naught is 1. And we have a true output on this statement here. Now let's suppose C is 0 and D is 1. Well, if C is 0, then C naught is 1. If D is 1, D naught will be 0. But again, we have another term that's actually all true. Finally, let's suppose that both are variables. And I say variables, I mean, the term is interchangeable with lines once you get into hardware. We want C and D to both be 1. But if C is 1, C naught will be 0. If D is 1, then D naught will be 0. And this whole statement will evaluate to 0. But hang on, we've seen this before. At least I'm assuming you have, probably in discrete mathematics, where you have, when the two inputs are the same, see, they are the same, then the output is 0. However, when the two inputs are different, as you can see here, C is 1, D is 0, C is 0, D is 1, the outputs are 1. So, what does that mean? That is what we call exclusive OR, sometimes abbreviated as E or X or. So, stepping back to our original algebraic reduction here, this whole thing can be reduced even further. So eventually we get B, A naught, and C, or A, C, E, or D, or C, X, or D, or C, exclusive OR, D. And let me just copy the original statement. A, not B, C, and D, or A and B and C and D not, or A not C, D not. Pardon me, I forgot the B there. A not and B and C and D not, or A and B and C not and D. Now look at how nicely that reduces. And it's much easier to see how this can be implemented in hardware.